It's a two-part session. So first I'm going to talk about what's involved in this in terms of encryption standardization approach for NVDIMM, and a little bit about background information on persistent memory technology. And then my colleague Fred Knight, I think everybody knows here, so he's going to talk about where we are on standardization approach. So a little bit of history here. So evolution of storage technology. So we see that on back in 20 years ago, that we had a clear separation between memory versus storage and compute and everything. But now that delineation is somewhat kind of blurred by the fact that we started using some of these memory devices for persistent storage, and also the storage has evolved over time, and so as a result, there's always dilemma whether am I dealing with a compute or a storage. So what's the NVDIMM? It's basically a DRAM, something running with DRAM memory speed, but with the persistent storage layer. So basically, what you gain out of this is a lower level of latencies and higher IOPS. Basically, the net result is that you have a drastic improvement in system performance. So this talk, the focus for this talk is on the device type NVDIMM-N on the left side, and the other two classes, for purpose of understanding, I have put in. So the access method differs across the two. The best of the best is probably the one in the middle, because it provides two access mechanisms, one with the DRAM, persistent DRAM, and another one with the block-oriented device access, similar to the -F type. So the N type is the one that we are interested in for this talk. So it has access methods, byte or block-oriented access method to DRAM. So we are going to talk about a little bit more about the technology itself. So what are the use cases? Traditionally the databases used to have the log accelerations, for which we needed some kind of caching layer and things like that. For in-memory databases, journaling is main thing that requires these kind of devices, and which offers reduced recovery time. And enterprise storage, we use a lot these devices, especially for storing of metadata, and also any vital configuration information or system wide information that we want to preserve over catastrophic power fail situations. And also it provides us a tiering layer, caching layer as well. And lastly, for high performance computing, checkpoint acceleration is one of the areas where it's being used. So technology overview. So basically, what is NVDIMM is basically a DIMM that provides a persistence layer, basically a methodology for it to save the contents of the SDRAM in case of power fail situations. So it can be integrated into the standard compute or a storage, and basically to provide supplement non-volatility for the DIMM layer. It relies on Byte-Addressable energy-backed function for saving the data, to preserve the data in case of power failure. So what does it mean by when we say that Byte-Addressable energy-backed function is? It's a composite layer. It consists of not only your SDRAM and also a NAND flash region for basically for the persistence, to offer the persistence. JEDEC standards 245C, it basically defines the interface specifications. It's called a BAEBI, Byte-Addressable energy-backed function interface. It specifies the configuration information for interoperability with NVDIMM-N class type of devices. So Fred is going to talk more about what's involved in extending that interface, and also the other portions of the standardization aspect. So this is a block diagram. It's of course from Micron product. I think there's a loose connection here. Apologies for this. So I don't want to touch this. So a system basically provides a 12-volt power source for the NVDIMM devices during normal operation when nothing has failed. And in case of power fail situations, there are two options. Either you have a system-wide supercap that's basically getting charged using your power management system, or option two would be that an additional, backup energy source, which is again, supercap that gets charged to through the power supply. I think whenever I touch the keyboard, it just goes off. So, in order to understand where this fits in, this illustration helps a little bit. So, at the bottom of the layer that you see the hard drive tier, which is persistent long-term archive, we know that it's a block level access and higher levels of latencies, and the mid level is the SSD tier, which is the technology offers again persistence, block level access and lower level latencies. The one on top is the persistent memory layer, byte level access and memory speed latencies. So, what's involved in NVDIMM-N? So, we wanted to, the standardization approach is mainly taking this device as similar to how we operate with self-encrypting drives. So, that's the objective here. So, if we consider NVDIMM-N device as a self-encrypting device, then that means what it has to do. It has to encrypt the data during a catastrophic save operation. So, catastrophic here means during a power file operation. And then it has to decrypt the data during a restore operation. So, we are going to see a little bit more on how this logic is. And the data is sitting in SDRAM plain text while it is in SDRAM, and it becomes a ciphertext when it is going into the NVM region, which is basically a flash memory backed up. And unlock the device with a password like a TCG storage protocol operates. And the standard that what we are deriving is based on Opalite, a subset under Opalite. So, storage system security is a subclass. So, there are three aspects of this standardization. One is that it involves extending the BAEBI specification to accommodate the security protocol definitions in consequence with the encryption scheme that we are putting together, and then extensions to TCG storage interface specifications, defining a security protocol typed block for handling interactions. So, Fred is going to talk about these. And the third one is floating in standard under TCG SSE for accommodating NVDIMM-N class devices. And this is a joint work between HPE and NetApp and other industry sponsors. So, this slide I am going to talk about a little bit about the cryptography scheme involved in these devices. So, basically on the left side is a host side interface that is outside of the boundaries of NVDIMM-N, and the right side block diagram represents what is happening inside the NVDIMM-N device. So, for encryption and decryption we use AES algorithm, and then it is a tweakable cipher stealing methodology. XTS is used because the reason is the boundaries, the byte boundary that what we are dealing with is not strictly aligning to a sector size, and so that is the reason we are using the block cipher mode. And then the RBG is used for basically generating the keys, encryption keys. So, when we talk about AES XTS, there are two aspects of it. One is the tweak value, which gets encrypted on the right side. On the other hand, there is also the actual cipher data that the actual plain text data that you want to encrypt. There is additional key is required. So, there is a dual stages when we are dealing with AES XTS. So, we generate the key using a PBKDF, password based key derivative function, and then for wrapping and unwrapping. So, after we encrypt the data, so we wrap the data encryption key is wrapped with a key and then stored it into the NVM, because that is required whenever we need to restore. We have to read the key in order to decrypt the data, and then the actual ciphertext which is already encrypted is also stored on the NVM, which is a flash region. I think that starts your session. Does it work?
Working? No, not working.
So, you can take this.
Okay, so now we want to talk a little bit about the actual standard changes that we're making. So one of the goals that we had was to reuse as much knowledge as we could, reuse as much existing code as we could. We didn't want to go off and do something brand new. We knew that TCG already had a way of encrypting data and keeping the data safe on devices. And while this gets stuck in a DIMM slot in a computer system, it really is storage. It's persistent data. And if you want to be able to have a way to ensure its destruction, then the TCG protocols are a great way to do that. So in SCSI, we have security protocol in and out. In the SATA devices, there's trusted send and receive. In NVMe, we have security send, security receive. So we've done the same thing for NVDIMMs. We've added a security out and a security in. And those commands have data buffers that transfer TCG data between the host and the device. And those data buffers are exactly the same, whether you're using SCSI, SATA, NVMe, or an NVDIMM. As much code reuse as we could, as much knowledge reuse as we could. So what we've done is added some registers onto the I2C bus. That's the bus that's used to configure and set up the DIMMs. When you install them in the system, the BIOS comes up and programs those registers. Well, there's a set of registers now for transferring the security information. So there were a bunch of registers where we could report errors already, and they had some free bits. So if you try and do something to the DIMM when security is enabled, but you haven't given it the key, then you're going to get a security error. And we could add that bit into some of the existing registers. In some cases, all 8 bits in those registers had been used, and so we had to create some new registers to be able to just indicate that there was an error. You were trying to do something illegal. And we had to create the new registers for transferring the data, because that's what the security protocol commands do. So within the NVDIMM protocols, within the BAEBI spec, we already had something called the typed block data that could be used to transfer data between the host and the device over that I2C bus. So we've extended that. We've added a new type of typed block data that is the security protocol. So there's 32 registers that you load up, and then you transfer the data from those 32 registers into the device. And you go through a loop to transfer as much data as you need to, 32 bytes at a time. And when you're doing the same thing, when you do a security in command, you do the command to transfer and load up the 32 bytes worth of registers, and then you read those registers. And then you do another command to load up the next 32 bytes, and you do that in a loop until you get all the data you're expecting from the device. So it's not quite as fancy and high-tech as we had in SCSI or SATA or NVMe. We don't have DMA. All we've got is this I2C bus. That's how you configure DIMMs. So that's the best we could do to configure them. So right now, the expectation is with the I2C bandwidth, it's not really fast. But you don't do configuration very often. You do it at power up, and then you're done with it. And we have got the I3C bus coming along, so hopefully the next generations are going to be getting a little faster. So basically, when you boot up and initialize, you've got to use the I2C path to supply the information. You authenticate, you supply the password to the device so that you can then enable the memory. And then you can use the DDR data path to do normal memory access. So if something bad happens, you lose power, then this is a persistent storage device, so we have to make sure all the data is persistent. But before it can get copied from the DRAM into the NVDIMM, we've got to go through the encryption engine. We've already supplied the password. We've already got the encryption key sitting there waiting. When the power goes away, the encryption process happens and your data is saved. So if somebody steals your device, just like with a self-encrypting drive, be it an SSD or hard drive, they've got encrypted data to deal with. It is saved, it is persistent. If they can't figure out the password and the key, then they can't get at your data. So it keeps it just as safe as it does with any other self-encrypting device. When power gets restored, you go back through the I2C bus, you supply the password. The password gives the device access to the key. The device can then restore the information using the encryption engine back into the memory, and then the memory gets put into an address range in the host that you can then access it, and you've got your persistent storage back again. So we've had to make modifications, first of all, to the BAEBI spec to create those registers, to create the type block data, to be able to transfer it back and forth. We're working in the TCG specs now, in the SIIS spec, to create a section that describes the specific requirements for NVDIMMs. There's a section there for SCSI, a section for SATA, for NVMe, and now a new one for NVDIMMs. That spec is also where the discovery process is described, how you find out whether a particular NVDIMM has encryption capability or not, and all of the error cases are described there. Those are isolated in the TCG spec and not in the BAEBI spec where the programming happens. The same is true with SCSI and SATA. It's all consistent. So we've looked at Ruby, we've looked at Opal, we've looked at Opal Lite, and none of them are quite perfect. So we believe there's going to be a subset of one of those because we've got a few things that are different. We don't need as many ranges for NVDIMMs as they have on hard drives. So is it just going to be one range, or maybe two, maybe four? We don't expect it will ever be any more than that. We're not sure that it will even be more than one range. We do know that we want a 32-byte password to be the minimum. We're not quite sure on the user authorities. How many of those do we want? And that's what is affected by the Opal, Opal Lite, or Ruby decision. You know, there are certain requirements for each of those, and these things are still being worked out. Right now, within those specs, there's some amount of data store that can be accessed over the transport bus, the configuration bus. Given that we have an I2C bus, we don't want to be transferring megabytes or gigabytes of data because it's going to be very slow. So we want to make sure that we limit the amount of data that's in that additional data store. There's also no point in MBR shadowing, a feature that TCG allows to have a duplicate secure copy of the master boot record. It doesn't make sense for an NVDIMM to be a boot device.
It also doesn't make sense for most boot devices.
There are some environments where it makes sense, but yes, in most cases, it doesn't.
By the way, how did your numbers align to the new TCG Enterprise 2.0, whatever it's called, that is Opal?
The question is about those features and the new Enterprise Opal Lite. We've looked at it, and they don't match up perfectly. That's why we think we've still got some definition to do to figure out exactly what we want these things to look like. So there are some interesting things that you have to consider when you think about NVDIMMs as storage. Right now, one of the things you do when you call support and you say, my system has a problem, they say, oh, well, let's do a power cycle. Let's just reset it. Pull the plug. Well, with NVDIMMs, when you pull the plug and you reboot it, you're going to get your exact same memory contents back again. It's not going to reset your memory. You also have to actually run some code to supply the password to the memory before the memory can be used. So if the only memory you have in your system is encrypted NVDIMM memory, you have no memory to execute that code in. So you have to come up with some other way to be able to process those instructions to feed the I2C bus with the code to turn on your memory. I mean, typically you'll turn cache into main memory, and whatever you do, whatever program you execute out of the BIOS is going to be run in the cache, but it's something different you have to think about in your system. Right now, when you boot up with interleaved memory, you know, which one's the odd bank, which one's the even bank, it doesn't make much difference because when the power comes up, there's nothing there. But now, if you've got persistent data contents, you need to remember which one was the odd bank and which one was the even bank. Otherwise, your data's not going to be the same as it was when you powered down. So extra things that you have to think about as the system builder. When you're doing firmware updates, these memory DIMMs actually have firmware in them. There are now security considerations around doing firmware updates on your memory. You don't want to supply some firmware with a new security bug that would allow someone to hack your encryption algorithm. So the BIOS has to think about some of these additional things when the system gets booted. They're a little bit different than traditional self-encrypting devices because it's your memory, but you do have to realize it's storage. It's not just memory. So in conclusion, just a couple of key takeaways. This is an important new device. There's a lot of workloads that can benefit from this. That it is a little bit different. It is a data retention device. You can't think of it just as memory. But as a data device, it does require the same protection that any SED does. A disk, a rotating media, an NVM card. So we hope that, in fact, this process will allow memory vendors to come up with the same kind of protocols that can be used everywhere, that we don't have to have a whole bunch of different vendor-specific protocols to deal with these kind of NVDIMMs. So at this point, questions? Well, guess we got a couple. Use the mic there.
Yeah, one important use case is for these NVDIMMs to be used really as memory, so you don't really care about the persistence. And so in that context, one feature that will be interesting here is that when you power cycle, when you bring up the power again, you simply reset the entire thing. So you allow using it again without unlocking or you can just go and overwrite and relock again later.
Why would you use a more expensive NVDIMM rather than just a regular
because
DIMM that would reset when it power cycles? I'm not...
Because for the use case where you want high density memory without really caring about the persistence, you really want to use it as memory.
It sounds like you don't need an NVDIMM for that. You just need a regular DIMM.
Well, I think Damien's talking about NVDIMM-P, not NVDIMM-N.
Okay.
Oh, he's talking about Optane, I think.
This is the one that writes back to flash.
Yeah, but so maybe NVDIMM-P, and the persistence is a bug in those use cases.
Yes.
So, but you still don't want to have that staying on your device when you bring it back up, because if it's stolen, you can actually see the memory content at the time it went down. So that's a security problem there. And having self-encrypting while you're using it, but just resetting the entire thing when you bring it back up would work as well.
Well, that's one of the other, we had the three different types there, NVDIMM-N, NVDIMM-P, NVDIMM-F. Well, the -P model is the one that is not battery backed. It is continually persistent. So if it's going to be a self-encrypting device, then every write to that device is going to go through the encryption path, and every read from that device is going to go through the decryption path. So that's a different type of device which has a different encryption model. Although the protocol to manage it, we haven't gotten to NVDIMM-P yet, but it's possible that it uses the same model, the TCG model. There are people who have proposed that we use a different model. We don't know yet. So we're still working on that one, still figuring that one out.
So the P has the best of both worlds. Yeah, but it's not ready yet for prime time.
P isn't persistent.
But having like a secure errors by default when you bring up the power, that would work for the persistence is a bug use case.
Yeah. Next.
I had two questions. One was the first gentleman said that you guys were using or were planning on using AES XTS for your encryption.
Yeah.
Have you considered adding at least room within the protocol for an authenticated standard like GCM or CCM?
Not.
Yes, yes, the TCG protocols have multiple. There are ways that you can specify the type of encryption key, that it may have to get added to the standard, or I can't remember the exact method for doing it, but there are ways to have multiple different types of keys.
It's not. This isn't about the keys. It's about like the individual blocks would come with additional metadata.
Right, but it's the algorithm that is used by the encrypting engine it's not hard coded. The standard doesn't require it to be AES. It requires there's a field in there that describes what the algorithm is that you're using. And so the standard can, the value 1 means this algorithm, the value 2 means this algorithm. So there's a table within TCG where you can have different algorithms that are allowed. And so
the default is
yeah, the default is, well, it's a field that you fill in the software and you supply it to the device. So it's hard to say it's a default because there has to be some software somewhere that fills the number into that field that says use algorithm X.
Right, but so within that protocol, there's like room within the transfer to support additional metadata per each block of memory, block of non-volatile data memory?
I don't know about that. You can specify different algorithms, but I don't know.
there's nothing.
Yeah, I can't. You don't have any extra data that goes, because this is memory. You read bytes, you write bytes. And so in terms of having extra data, the metadata that would go with some chunk of memory, I don't know of any way to do that.
Okay,
So.
I was just wondering. My second question was faster. It's just about how long does it take per gigabyte to get your data back out after a power loss event?
Well, I think it's in the tens of seconds ballpark. And it's not the encryption decryption that takes the most time. What takes the most time is using the I2C bus to
Right.
communicate the information to the encryption engine so that it can actually do its work, which it does relatively quickly.
Gotcha. Thank you very much.
So when hearing that you're only encrypting when transferring to the backing flash, I'm wondering a little what the threat model is, because that seems to be very weak against warm boot attacks, hot swap kind of attacks where you still get at the memory content while it's not actually on the flash. So what's the threat model this is built for?
The idea for the threat model is the same as a hard drive. That if you pull it out, take it out of the system and take it to another system, you're not in a warm boot or warm situation. You've gone through a cold reset.
Well,
If if somebody steals my laptop and I've got a self-encrypting drive in it and I've left it in a standby state, if they can get at it while the power is still applied, it's that kind of threat model.
Yeah, well, I mean, the laptop is kind of a special case with the suspend to RAM, but when we were talking about disks a couple of years ago, we exactly had those attacks where you had an SSD or hard drive back in the days, doesn't really matter, that people took out, reconnected it quickly enough that the key would still be in memory and they could get at it. And for a system where the prime model of operation is that your unencrypted data is always in DRAM that is backed by a capacitor or battery to keep it alive long enough that we can actually store it on flash, these attacks become very, very real. Because the whole point of the device is to keep it in memory for a while after the power connection is removed.
And it's the same model. The threat model is the same model that is used with the self-encrypting devices.
Yeah, and for drives, the vendors have worked that these attacks don't work, or at least are claimed to not work. That when you take the SSD out of a live system, steal it, cut the cable, plug it really quickly into your attack device, that you don't get at the data. While for an NVDIMM, if an attacker is available to quickly plug it and get at the data, resupply the power, this looks very, very real to me.
But if they're reapplying the power, then that means the power has been lost, in which case you have to go through the authentication sequence again. Because the data's gone. You remove the power, that DRAM memory loses the data. The unencrypted
again,
versions of it are gone.
This is about the timing between losing the external power supply and losing the energy in the internal capacitor, battery, whatever's powering the write back to the flash.
Right, right.
Yeah, and I wonder if, yeah. Yeah, and I just wonder if that's part of
Yeah, that's
mitigations or.
yeah. You've got the timing window during which the supercap or battery is being used to do the encryption and write the encrypted data. So, yeah, there's a little bit different window
that's
there. So,
potentially a huge window with a large DIMM and a slow flash.
and the NVDIMM-P would solve that problem because it's encrypting on the fly, decrypting on the fly. There's no time window. So that's one of the advantages to the -P model.
So I was just wondering, if the I2C is what takes a lot of the time, could you preload the data that you would send over I2C into the DRAM, knowing that it's going to just be overwritten?
You could, but you couldn't access it because you can't configure the device to give you access to the DRAM until you go through this process. So it becomes a catch-22.
Oh, you can't even write to it before it's initialized?
If the memory's not configured, there's no address on the DDR memory bus until after you configure
You
it.
need to run SCPI to know that you have that memory at the very least.
I'm sorry, I can't hear.
Yeah, guys, why don't we close out this session, and I think, are you guys staying around?
Yeah,
a little bit?
around for,
So,
an hour.
So we've got about an